thousands of planets have been discovered so far, and there's a huge range of different types of planets. There are small planets, big planets, hot planets, cool planets, oddly shaped planets. But what is the hottest planet that we have discovered so far? Well, it's called KELT-9b, and it's actually hotter than some stars. So in this video, we're going to have a look at the planet itself, why it's so hot, and some consequences of being, well, hotter than some stars. So the most obvious thing here is actually that it's so hot that it might actually be evaporating. So it doesn't mean it's going to last particularly very long if it's evaporating, but it's so hot that it might look like this and may actually have a comet-like tail around as it orbits the star, because it's essentially evaporating in a not necessarily a similar manner to a comet, because they don't get as hot, but it's basically evaporating parts of its atmosphere. So let's put this planet in context of stars, because it's hotter than some stars. It's kind of size-wise is quite a large planet as well. So in the context of the Sun and red dwarf stars, it sits in between. So the Sun has a temperature of about 5,700 Kelvin. A red dwarf star, which is smaller and cooler, has a temperature of about 3,000 Kelvin. And KELT-9b is about 4,000 Kelvin. So the average surface temperature of this planet is about 4,000. So it's actually hotter than your small red dwarf stars. And actually, red giant stars, whilst they are bigger stars, their temperatures are kind of comparable to a red dwarf. They're just smaller. So this is a very hot planet, hotter than some stars, and actually not that much cooler than our own Sun. So if we go to the HR diagram, which is a diagram plotted of stars that have been detected and measured, you've got the luminosity on one axis and then you have the temperature on the other. And you can see in this box that I've highlighted here, all of those stars there are actually cooler than this planet that has a surface temperature of about 4,000 Kelvin. So these are red dwarf stars, red giant stars, and the size doesn't necessarily matter too much. It's actually their temperature. So there's a huge amount of stars that fall into this category that are actually smaller, or not necessarily smaller, but cooler than our planet. So size-wise then, if we go and have a look at the actual size, they're almost comparable, or it is almost comparable to a red dwarf star. So a red dwarf star would be about, typically, I don't know, a quarter the radius of the Sun, and then this planet is about 1/5, so 0.2 the solar radius. So it's a very large planet. Not only is it very hot, it's very large. So it's almost comparable to a red dwarf actually, but it's a planet, not a star, which is important to note. Now here, you've got some hot Jupiters. So what was done here was some modelling was carried out, and it was to predict what the clouds might look like on hot Jupiters depending on their temperature, which is along the top there. So it goes from 1,000 Kelvin to 2,100 Kelvin, and then each row is a different composition what those clouds might be made of, and it gives you an idea of how the clouds might look on those hot Jupiters. Now the key thing to note here is along the top. Typical temperatures of hot Jupiters are 1 to 2,000 Kelvin. This is considerably less than this hot planet we have. In fact, the hot planet we have is twice as hot as probably your upper hot Jupiters really. So it's a very, very hot planet, and it almost sits in a category on its own, which we will classify as a ultra hot Jupiter. So this sits outside of our typical hot Jupiter, which are very large planets very close to their star. In fact, that's quite similar to KELT-9b. But it's so much hotter that it's in its own category. So although it is close and it is hot, it's classified as an ultra-hot Jupiter because its temperature is just so much more greater than a typical hot Jupiter, which actually we found lots of. Probably one of the most abundant planet types is hot Jupiters because, well, they're easy to find basically. So why is it so hot? Well, the star that it orbits, which is known as KELT-9, is quite a large star. It's also quite a hot star. So it's just over 2 times the radius of the Sun and about 2.5 times the mass of the Sun. So it's quite a large star. It's got a temperature of about 10,000 Kelvin. So it's almost twice the temperature of the Sun. So it's a large star very hot star. So because it's very large, physically quite large, and very hot, it's giving out an enormous amount of energy in comparison to the sun. So it's giving out lots more energy. And that in itself would make the planet hot. So if it was at the same distance to the Earth, it would be much hotter anyway. But that's not the case. It's actually very close to its star. So it orbits in just under 1.5 days. So it's on a very close orbit. When you compare to 365 days, which is our orbital period, this is a very close planet to its star. And in the context of our own solar system, well, it's less than 1/10 the orbital radius of Mercury. Now, Mercury is a hot planet. It's close to our sun. But this planet is 1/10 the distance to its star, what Mercury is to the sun. So that's why it's so hot. It's a very large and very bright or hot star, and the planet is incredibly close as well. So those two things together is what add up together to make this the hottest planet we've discovered so far. Now, because it's so close, it's also expected to be tidally locked. This is where one side is always facing towards the star. The tides from that star have slowed it down so it doesn't rotate fast anymore, and it takes one orbital period to do one rotation on its axis, which means that the same face is always facing inwards. It's the same for our moon, the same process has happened there. But planets close to their star are typically tidally locked, and if they're not, they will be slowing down to become tidally locked. So in time, they will always end up in this way. Now, because of that, you've got a side that is in permanent daylight. So you've got a permanent day side and a permanent night side. And there's a huge difference in temperature between that. So on the side that is always facing towards the star, it has a temperature of about 4,500 Kelvin, compared to 2,500 Kelvin on the night side. So whilst they're both hot, there's a big difference in the temperature, and that in itself can drive quite strong winds. So it's heated on one side, that causes the rising of the atmosphere, which then circulates round to the night side, and that actually transfers heat. So although there's a big difference between the two sides in temperature, the fact that the night side is still 2,500 Kelvin, which is still hotter than most hot Jupiters, is because these strong winds are circulating that heat around to keep the night side hot, even though no direct energy from that star is falling on that particular side. Now, because the permanent day side is so hot, any hydrogen molecules in its atmosphere, which could likely be quite common given that it's a Jupiter-sized planet, are going to get torn apart. There's enough energy there to break the bonds, and then you end up with hydrogen atoms instead. And because you've got those strong winds circulating and basically moving the atmosphere and gases around to the night side, they move round to the night side, and then on the opposite side, it's actually cool enough for them to recombine. So the hydrogen atoms then recombine back into molecules, and then the cycle goes around again. So you're on one side, these molecules are getting torn apart because the energy is sufficient and the temperatures are high enough. But on the night side, they're cool enough to kind of recombine. And this is kind of one of the only planets where this is thought to be occurring because it's just so hot. Hotter than most stars. Well, not most stars, but some stars. Now, it's on a very close orbit. And we know that these hot Jupiters and presumably ultra hot Jupiters like this one cannot form where they currently are. There just isn't enough mass in the disk to form there, and there's a few other problems basically with the formation process. So they have to form further out and then migrate inwards. And when planets are forming, they typically form in a disk around a star. And there's an interaction between the planet and the disk. So this disk is gas. The disk doesn't orbit at the same velocity as the planet. So there's a kind of interaction there, a drag on its orbit, which can mean the planet migrates inwards. So maybe that's one process that actually moved it in closer to the star. But the bigger problem is it's on a polar orbit. So if it was in the disk and it migrated inwards, it should still be orbiting in the same direction that the star rotates, but it's not. It's actually orbiting around its poles, which is very unusual. So that's not where planets can actually form. So there's a process known as gravitational scattering, and this is where planets pass by one another very close, and their gravitational interaction at that point is quite strong, and they can actually alter each other's orbits. Now, if they're in that disk together and they migrate at different velocities or they move around whilst they're still forming, they can pass by one another very close, and it causes this gravitational scattering effect. Now, one thing that does do is it can change their orbit. So typically it may elongate an orbit. So one of the things we suspect when we find a very elliptical orbit of a planet is that, well, it could have had a gravitational scattering event. There could have been two planets passed by each other very close, and that has then scattered its orbit to a more elliptical one. But another consequence of that actually is that it can scatter it in the inclination. So if all the planets are on the same plane orbiting the star, then what can happen is it can knock it out on inclination, so it can actually make it on a polar orbit. And that is a consequence of gravitational scattering, as well as making it more elliptical. Now, it's worth noting that if that did happen, it would have been on an elliptical orbit to start with, but the gravitational tides from the star would have made it more circular over time, the same way that it's actually made it tidally locked. So it would be on more of a circular orbit as time goes on. But we don't necessarily know exactly how it got where it was, but this is one of the processes that can form those types of orbits. So thank you for watching, and if you enjoy, then check out some of the other videos.